So we have seen the master slave flip-flop, SR flip-flop, right? And we had seen what is the disadvantage of having an SR flip-flop. And then this we saw the timing waveforms, right? And how JK flip-flops are and how they are advantageous, and zeros and one catching, and the edge triggered flip-flops, right? So all of these we got to saw. Edge triggered, level triggered, so all these types of parameters were discussed, and we even saw how we can get characteristic tables, right, and characteristic equations, and yeah. So one topic that we had to discuss was with regards to D flip-flop, okay, and how we will be creating it using CMOS pass gates and inverters. So this is a standard diagram, okay, as to how your D flip-flop is employed, okay, how we create a D flip-flop using CMOS pass gates and inverters. Now, as we all know, okay, this is our structure of D flip-flop, right, where one of the inputs and the inverted input is given as input to the other gate. The rest of the second stage of our gates are cross coupled, okay, which means one output is given as the input and the other's output is given as part of the input. So here you will be getting your Q bar and Q. So ultimately your D is nothing but whatever input is given, the same thing you get at your output, provided with certain delay. And now that delay is because of this inverter and because of this AND gate and this NAND gates. Okay. So similarly, what we will be doing is we will be developing a D flip-flop, okay, using CMOS pass gates and inverters. So we do have inverters here, okay, we do have inverters here. Now, the only thing that we'll be looking into is this transmission gates, okay. PG is nothing but your transmission gates. It's a combination of your NMOS and PMOS. NMOS, as I've told you previously, is good at conducting zeros, and PMOS is good at conducting ones, which is the high value. So wherever you see this bubble here, okay, that means it's actually your P type of transistor, and wherever there is no bubble here, okay, that's an N type of transistor. So ultimately, what we are trying to do is we are trying to combine both P and N, okay, and the structure goes like this. Okay, so okay, so here at one side you will have a bubble, and at the other side you wouldn't have a bubble. So this one is actually representing your P type, okay, and the other one is actually representing your N type. Okay. So here, as we give our input, okay, if you can see here, we just have one input, and the inverted input is given to the other gate. Okay, so we do need to have a common thing called clock. Okay, so you have one input here as clock, and the other one is also a clock here. So one common thing is clock, and the other one is your input, and the inverted output is the input to another gate. So which means we have one input, okay, and we have one clock for four inputs, two inputs here and two inputs here. So for four inputs, 2 plus 2, we just have, for four inputs, we have just D and clock. So clock is common to one of the terminals here and one of the terminals here. And D is common to one of the terminals here and here. Okay, so that's the concept. So here we give our input D. Okay, clock is commonly given to both our gates. So during passing the input, okay, if in case it's a low valued input, then it will pass through an NMOS. If it's a high valued input, then it is going to pass through your PMOS. Okay, so ultimately selection is going to happen here between these two, and that is going to decide based on the clock. Okay, so if it is a clock, then this is going to be enabled. So ultimately you should know that, clock signal is enabling or disabling your gate of your transistor. Now as you all know, okay, your transistor, it does have something called source. Okay, then we have the gate, and then we have a drain. So this concept, all of you are clear, right? Do you all remember this concept? Yes.
Yes,
Fine. So what we are trying to do here is, this is acting like a gate. Okay, the clock signal that we are giving is nothing but a gate signal. Okay, so if the gate is enabled, which means if I turn on the gate, that is when you will find that electrons are passing from one end to the other, right? And the current is actually in the opposite direction, right? Okay, so these clocks are actually acting like a gate input, right? So I give the input here based on the clock. Okay, it decides as to where the input is going. So if this is enabled, then the input passes through. Then this is an inverter, so you get an inverted output. Suppose in the other clock, okay, let us say that okay, so let us take this as 1 and let us take this as 0. So during the first phase, okay, so let us say that the clock is high here, and this is the clock bar, okay, the 0 phase. So during that, what is going to happen is, okay, it is going to pass through PMOS, and ultimately passing through an inverter, okay, and we are getting the inverted output here. Now that inverted output, again, if I pass through an inverter, what is going to happen? Q bar is going to become Q, okay, so which means my D is equal to Q, and that is how, I get my output here. So ultimately what we are trying to see here is, we are just using two types of transistors here, which is NMOS and PMOS. Okay, here also NMOS and PMOS, and we are using two inverters to nullify them. Okay, so which means if I get a Q here, Q will pass through, and I will get Q bar will pass through, and I will get ultimately Q. Okay, this is my interest. So if this happens, okay, so ultimately I can actually pass through. Okay, I can pass through. If clock is enabled, it will pass through NMOS. If clock bar is enabled, then it will pass through PMOS. Okay, so I can either obtain my output here at this point, or I can obtain my output at this point. Okay, fine. When clock signal is high, then TG1 is closed. Okay, so we have TG1, okay, which is your transmission gate 1, and we have transmission gate 2. Okay, so when the clock signal is high, then TG1 is closed, and data at D is passed to the output TG2. Okay, so at that point of time, TG2, because clock will be the same, right? So if I give 1 here, then 0 will be here. So high means it will enable this. Okay, so data will pass through. Okay, data will pass through your TG2. Fine. So TG2 is open when the clock goes low, then TG1 becomes open. So in the next phase, as I showed you the clock waveform, so in the next phase, if this is closed, this will be open. Okay, because the clock is connected here, and you can see that clock bar is connected here. So either one of them, okay, either one of them will be enabled. See, you can just observe here, the bubble, the clock bar is given to the bubble. Okay, but here the clock bar is not given to the bubble, but then it is given to NMOS, right? So similarly, here clock is given to the bubble, and clock here is given to non-bubble, which is NMOS. So ultimately, I can decide as to which switch to open, either to open TG1 or to open TG2. So at one point of time, say if this is closed, if this path is closed, okay, when I say TG1 is closed, which means it will not pass through this. Okay, it is going to um, select just one here. Okay, so it is like, complementary to each other. If TG1 is functional, TG2 will be off. If TG2 is functional, then TG1 will be on. So this happens based on the clock signal. So as I showed you the gate signal, right? So the gate signal can actually enable and disable the transistor. So once the transistor is disabled, it means that the data is not passing through. Can now someone tell me, for an NMOS to be disabled, what should be my gate potential? Should it be high or should it be low? If I give a high value at the gate, is my NMOS going to turn on or off?
Sir, it will turn on.
Correct. So if I give a high value, NMOS will turn on. So if I give a low value, then my PMOS will turn on. So based on that concept, okay, you can see that the connections are done for PMOS1 and for NMOS. So ultimately it will pass through NMOS, it will come here, then complemented version. Okay, then it will pass through my um, gate which is being enabled, and then finally I will get my output. So it is like a continuous loop here. Okay, you can find that it's a continuous loop, just that the data either passes through NMOS or passes through PMOS based on the clock whichever is selected. So it's a feedback loop, yeah, which is now closed. Data is therefore latched into the circuit. So which means it is like a latch which is held on in this particular loop. Just a moment. Yeah. So whatever we discussed so far, okay, I have put up in the form of explanation so that it becomes easy for you to understand. Figure A shows the use of transmission gate as a feedback element in level triggered latch. Always remember, okay, your latch is level triggered. I think you would have seen that in my notes as well, right? Latch is a type of level triggered. You have seen that in my notes that I've shared. The equivalent non-TG version using logic gates is also shown in figure B, the one you saw with AND gates and NAND gates. And again uses many more transistors than the transmission gate version. Now see, the one that we saw with transmission gate is not the final one, right? So which means we will have more complex things than this final one, okay? Which means circuit can be designed not only using your transmission gate, okay, but then with the other logic gates also it can be implemented. That is what I'm trying to say here. As a result of this, all CMOS flip-flops are designed using space-saving TG technique. This is very important. Why? If I ask you a question as to so as I was mentioning, it's not just the final version. Okay, the transmission gate that we have is not just the final version. Okay, but then we can also develop it, okay, using various other techniques. Okay, to produce a JK with CMOS transmission gate, it is necessary to add appropriate circuitry to a transmission gate based D type. Okay, so ultimately, any type of latch or flip flops can be developed with the help of your normal circuitry. Now that can be done with the help of equations, right? So once you have the equation, as you all know how to develop a CMOS circuit, where PMOS is at the upper side and NMOS is at the lower side. PMOS is connected to VDD and NMOS is connected to ground. So ultimately, based on the serial and parallel combination that we discussed, right? So any CMOS circuit can be implemented. Hence, CMOS JKs, okay, are more gated than D types. It is for the reason that CMOS gates use the D type as the basic flip-flop rather than J2. So D flip-flop, what I'm trying to say here is this D flip-flop is the most basic version, okay, of a flip-flop. That's because whatever input is there, okay, the same thing we get it as an output. So I don't have to have any complex circuit for that. But instead, I can just have a simple cross-coupled connection, and the same output will be uh, connected back again, right? So this was about your D flip-flop using CMOS pass gates and inverters. So any doubts here, students? Any doubts here? Can I proceed with the next one? Okay. Thank you, Margaret, for that reply. So with this, we actually complete our third module, okay, and we'll be entering into our fourth module, okay, which is nothing but your flip-flop applications. Okay, now that we have seen a lot of things, okay, that is with flip-flop and its conversions from one form to another form, right? We have seen a lot of things as such. So now we will be looking into something where how we will be employing them. So which means how we will be using them, and how is it going to benefit us, okay, in order to carry out certain operations. Okay, fine. So what do you understand by a register? A register is a collection of flip-flops, okay, which is uh, just a moment, please. Okay, so a flip-flop, collection of flip-flop is nothing but called a register. So which means it can hold a lot of data. Okay, so that is meant by a register. And what are its functions? It can hold information within a digital system so that it is available to the logic elements during the computing process. So why do you think we need a register? Is it necessary to have a register? Yes,
Yes,
students, is it necessary to have a register?
yes, sir.
Why is it so?
To hold the data.
Yes, so data is very much important, right? So we cannot process things without data. Nothing is processed without data. So data is taken as the basic input, and with data, a lot of processing is done. So which means if I have to compute things, then data is needed. So we need flip-flops, and this collection of flip-flops together is called as a register. So the function is to hold information within a digital system so that it is available to the logic elements during the computational process. Each combination of stored information is known as state or content of the register. So we are coming up with new things called a state. Okay, state is nothing but, remember the block diagram that we saw, right? One had state, and the uh, the initial part of sequential circuits. We discussed about a block diagram, right? The output where one of the outputs were called state, right? So we will see deep into that. Each combination of stored information is known as state or content of the register. So whatever data is inside the register, it is called as a state. Now here for your first topic, we will be looking into shift registers, okay, which is nothing but moving data from one point to another point. And there are four types, okay. There are four types of shift registers, which is PIPO, SIPO, PISO, and SISO, which is parallel in, parallel out, serial in, parallel out, parallel in, serial out, and serial in, serial out. So based on the type of inputs and the type of outputs, we decide as to what type of shift register this is. Registers are capable of moving information upon occurrence of a clock signal. So clock is very important here. So once I have a clock signal, I will be able to actually move data from one point to another point. And here you can see that there are, based on the movement of data, two important major categories. One is unidirectional and the other one is bidirectional. So unidirectional means it moves only in one way. Bidirectional means it can move two ways. Right. So movement of data, I think you all know, is going to be in the form of parallel or serial, right? So just have a look at it. So these are the two types, which is parallel and serial. So parallel means data goes simultaneously, but serial means the data goes one by one. It goes bit by bit. All 0 or 1 symbols are handled simultaneously. They require many lines as symbols are being transferred. So we need more parallel lines. We need more lines connected between one point to another point. Serial involves symbol by symbol availability of information in a time sequence. So whenever there is a clock, then there is a bit that is being passing from one point to another point. So these are the four combinations that I was talking about, right? Which is your serial in, serial out, serial in, parallel out, parallel in, parallel out, parallel in, serial out. So accordingly, it is called SISO, SISO, SIPO, PIPO, PISO. Okay, so these are the four types of registers in which the data can be represented. So the first one that we are going to see is your serial in, serial out, unidirectional shift register. Okay. Now these topics are important because it is going to come up in your examinations as well as your CIE. Okay, so just have a glance at it, and you'll be able to understand as to how we can employ these. So for this, as I told you, we are basically using the flip-flops. Ultimately, register is a combination of flip-flop, right? So if these flip-flops are put up together, okay, then it can hold data, and ultimately together it is called a register. So you can see that your data goes in here in the D flip-flop. There is a clock that is connected. First, try to understand the structure, how it is. Okay. So you have 4 bits here, okay, each capable of handling 1 bit. Okay, so 1, 2, 3, 4. So as soon as this passes through, okay, it will check for clock. If the clock is enabled, then only the data passes through and it comes to Q. Okay. Ultimately, what is going to be D and Q? Suppose I give 0 in D. What is going to be my Q, students? Let's say I give D as 0. Okay. So what is it going to come up at Q?
Sir, 0.
0. So which
Zero,
means,
sir.
yes, thank you. So which means we are going to receive the same type of output, whatever input was given. So here we are going to get the complemented version, right? So this is going to pass through. It's going to check for clock, then only the data is handed over to Q. So it is moving from one flip-flop to another flip-flop. So it's called serial in and serial out. So here it passes through. Okay, it passes through, then it passes through, and then I get here output bit by bit. Okay, so let's consider this as first stage, the second stage, the third stage, and the fourth stage. So the data keeps passing, you know, in this fashion. So yeah, so whatever data I'm giving here, let's say I'm giving 0, 1, 0, 0. Okay, so I will be getting the same output here. Okay, bit by bit. So serially it goes, bit by bit. Ultimately, it's going to check for clock. Okay, if the clock is enabling that, then only it is going to function. If not, it will not function. Right? So that's why we have the term called serial in and serial out unidirectional shift register. That's because the data is passing from the left hand side to the right hand side. It cannot pass the other way, which is from the right hand side to the left hand side. Okay. So if a question is asked based on CSISO, then you'll have to represent this diagram, okay, and you'll have to write an explanation as to how it is functioning. Figure shows SISO unidirectional shift register constructed from positive edge triggered D flip-flops. Most of the time, students, we will be considering positive edge triggered values only. Okay, most of the time, for the purpose of simplicity, okay, we will take only the rising edge of the clock. Okay, rising edge of the clock, which means values moving from lower value to a higher value, 0 to 1. So that's called a rising edge, or it is also called as a positive edge. The Q output of each flip-flop is connected to D input of the flop to its right. Okay, the flop to its right. So the output of the previous stage is the input in the next stage, right? So that is what it is. The control inputs of all the flip-flops are connected together as a common clock. Okay. So we have a common clock, and that is connected to all the flip-flops. Suppose my clock is 0, then everything is nullified, which means it is all disabled and it will not be functional, which means I cannot pass data. When the positive edge of the clock occurs, the content of each flip-flop is shifted from one position to the other towards the right. So which means at every clock cycle, there is a shift of one position towards the RHS. So data will keep moving towards the right hand side. The content of the leftmost flip-flop after the clock signal depends on the signal value on the serial data in line, and the content on the rightmost flip-flop prior to the clock is lost. So which means whatever content that was there on the leftmost flip-flop after the clock signal, okay, it depends on the signal value of the serial data in line, and the content on the rightmost flip-flop prior to the clock signal is lost. So which means as soon as there is a clock signal, whatever value was there at the output side is lost. Okay, and whatever was there previously, okay, in the third stage gets moved on to the fourth stage. Okay, so as the clock keeps moving from 0 to 1 and 1 to 0, okay, basically we are looking at our positive edge triggered flip-flops. So which means if the values are moving from lower to the higher, only those are considered, and during that point only there is a transition of data from one stage to another stage.